At the end of this video, you should be able to recognize the difference between the scientific and ordinary definitions of work, define work by relating it to force and displacement, identify where work is being performed in a variety of situations, and calculate the net work done when many forces are applied to an object. Chapter 5, Section 1, Work. Definition of work. Many of the terms you have encountered so far in this course have meanings in physics that are similar to their everyday meanings in life. In its everyday sense, the term work means to do something that takes physical or mental effort. But in physics, work has a distinctly different meaning. Consider the following situations. A student holds a heavy chair at arm's length for several minutes. Or, a student carries a bucket of water along a horizontal path while walking at constant velocity. It might surprise you to know that as the term work is used in physics, there is no work done on the chair or the bucket, even though effort is required in both cases. We will return to these examples later. Work is done on an object when a force causes a displacement of the object. Imagine that your car, like the car shown in figure 1.1 on the screen here, has run out of gas and you have to push it down the road to the gas station. If you push the car with a constant horizontal force, the work you do on the car is equal to the magnitude of the force, represented by F, times the magnitude of the displacement of the car. Using the symbol d instead of delta x for displacement, we define work as work for a constant force as W is equal to Fd. Work is not done on the object unless the object is moved with the action of the force. The application of a force alone does not constitute work. For this reason, no work is done on the chair when a student holds the chair at arm's length, even though the student exerts a force to support the chair. The chair does not move. The student's tired arms suggest that work is being done, which is indeed true. The quivering muscles of the student's arms go through many small displacements and do work within the student's body. However, work is not done on the chair. Work is done only when components of a force are parallel to a displacement. When the force of an object and the object's displacement are in different directions, only the component of the force that is parallel to the object's displacement does work. Components of the force perpendicular to a displacement do not do work. For example, imagine pushing a crate along the ground. If the force you exert is horizontal, all of your effort moves the crate. If your force is at an angle, only the horizontal component of your applied force causes a displacement and contributes to the work. If the angle between the force and the direction of the displacement is theta, as is shown in figure 1.2 on the screen here, work can be expressed as follows. W, work, is equal to F, force, times displacement, d, times the cosine of theta. So W is equal to Fd cosine theta. If theta is equal to 0 degrees, then cosine of 0 degrees is equal to 1, and work is equal to force times displacement, which is the definition of work that was given earlier. If theta is equal to 90 degrees, however, then cosine of theta being 90 degrees is 0, and therefore work is equal to 0. And no work is done on the bucket being carried by a student walking horizontally. The upward force exerted by the student to support the bucket is perpendicular to the displacement of the bucket, which results in no work done on the bucket. Finally, if many constant forces are acting on an object, you can find the net work done on an object by finding first the net force on the object. Work has the dimensions of force times length. In the SI system, work has a unit of newtons times meters, represented as capital N times M, or joules, represented by capital J. To give you an idea of how large a joule is, consider that the work done in lifting an apple from your waist to the top of your head is about 1 joule. The sign of work is important. Work is a scalar quantity and can be positive or negative, as is shown in figure 1.3 on the screen here. Work is positive when the component of force is in the same direction as the displacement. For example, when you lift a box, the work done by the force you exert on the box is positive because the force is upward, in the same direction as the displacement. Work is negative when the force is in the direction opposite the displacement. For example, the force of kinetic friction between a sliding box and the floor is opposite to the displacement of the box. So, the work done by the force of friction on the box is negative. If you are very careful in applying the equation for work, your answer will have the correct sign. Cosine theta is negative for angles greater than 90 degrees, but less than 270 degrees. If the work done on an object results only in a change in the object's speed, the sign of the net work on the object tells you whether the object's speed is increasing or decreasing. If the net work is positive, the object speeds up, and work is done on the object. If the net work is negative, the object slows down, and the net work is done by the object on something else.
Energy can be defined as the ability to do work. So to understand energy, you need to understand work. Work is the product of the force on an object, the displacement of the object, and the cosine of the angle between them. Since the cosine can be positive or negative, the resulting value for work can be positive or negative. For instance, if you pull a toy car across a level surface as pictured, the work is positive. The effect of your work should be to speed the car up. Notice that the force, if broken up into components, has a rightwards component. This rightward component agrees with the displacement of the car. However, if you pull as pictured here, you will tend to slow the car down. Since the force is to the left while the motion is to the right, the work done is negative. Again, the force and motion are in opposite directions here, so the work will once again be negative. The work will have the effect of slowing down the car. Here, the force and displacement are in the same direction again. Work is positive and the car speeds up. You can remember this two different ways. First, you can simply picture the force as being in the same direction as or in the opposite direction to the motion. Opposites are negative, so the work is negative when the force opposes the motion. Alternatively, you can visualize the angle between the displacement and the applied force. When the cosine of this angle is positive, the work done on the object is positive. When the cosine is negative, the work done on the object is negative. One last thing to remember is that when the force and the displacement are at right angles, no work is done.
At this point, you should be able to recognize the difference between the scientific and ordinary definitions of work, define work by relating it to force and displacement, identify where work is being performed in a variety of situations, and calculate the net work done by many forces being applied to an object.